14.72. An object with a mass height h, mass m, and uniform cross-sectional area A floats upright in a liquid with the density rho. A. Calculate the vertical distance from the surface of the liquid to the bottom of the floating object at equilibrium. B. A downward force with magnitude F is applied to the top of the object. At the new equilibrium position, how much farther below the surface of the liquid is the bottom of the object than it was in part A? Your result in part B shows that force is suddenly removed. The object will oscillate up and down in simple harmonic motion. Calculate the period and motion in terms of density rho of the liquid in the mass m and cross-sectional area A of the object. You can ignore damping due to the fluid friction. Okay, so for part A, V equals, so that's our volume, equals height times area. So then force of buoyancy, F of B, equals rho G H times A. And then our force of B also equals weight, and weight equals mass times gravity. So then we can say that rho G H times A is equal to mass times gravity. Gravities will cancel, and we'll get that our height is equal to mass divided by rho times A. So A. B, we can say our volume is equal to height plus x, which is some distance, we don't know, times A. So then force of buoyancy now equals rho G times H plus X times A. So then force total, net force equals mg plus F, and FB equals force total. So rho G H plus X times A equals mg plus F. Okay? Then our X is going to equal mg plus F divided by rho GA minus H. We can plug in our H from above, and then we'll get that X equals force divided by rho GA. Okay, for part C, period equals 2 pi times the square root of n divided by k, and net force equals negative k times x. So then our net force equals negative rho G X times A from plugging in, and negative kx is equal to negative rho G X A. So then k is equal to rho G A, and our period is equal to 2 pi times the square root of n divided by rho GA.